In the next video, we'll explain about the questions in your textbook or on your notes. I would recommend you to pause the video now, do first 2 pages maybe, from question 2, 3, 4, 6, and 7, and then you can check the answer, and after that you can start to do 8, 9, 11, 12, 14, and then you continue to watch the video again. Okay, question 2. First of all, you have to recall the idea of net force, and I would strongly recommend you to draw on the diagram that is a force pulling towards the left, one pulling toward the right, caused by the 2 charges. So I name it Q2 and Q3, and the one that you're actually caring about in the middle is Q1. So it will be the best if you can use the notation more efficiently. So at the end of the day, what you have to do is simply applying the force Coulomb's force formula on both forces. So that will be K Q1 Q2 over the distance square. So you just have to apply them correctly, and be careful once again is cm, so you have to use the SI unit, and in that case that means you have to change it to meter. That's why you will find 10 to the power of -2 here. At the same time, just a tiny mathematics tips for you. It would be probably the best if you can ignore the power first. That means you ignore this one, this one, this one, this one, this one, and this one. You do it later. So what you could handle first could be the coefficient, which is this one, and then actually inside here you may want to do the 4 divide 4 square first minus the 3 divide 2 square first, and then you can work out the power directly. So then this is the answer. What I find is that since I name F2 minus F3, so I actually believe the net force was pointing to the left, but then you can see that eventually I find out that the answer is actually negative, because simply the value of this is smaller than the value of this. So that's why it's negative, and that's why the net force is actually pointing to the right. Question 3, we have the same question, but now it's asking you for a particular position where it is in equilibrium. So the first sentence I'll expect you to write is when the forces are the same. So F2 equals to F3 if you're referring to these 2 forces. And then again, you can use the Coulomb's law, and which is K Q1 Q2 over distance square. Like the example that we did, you would want to set a unknown for the distance, and the other distance you don't want to create a new variable, so call it 6 minus x, because the total is 6 because of 4 plus 2 is 6. So simply solving is just some algebra work, and you have to solve a quadratic equation. I'm sure you know how to do it. If you don't know, you can ask me, and the answer is 3.22 cm. The next question is the most painful, okay, because it takes a lot of steps. First of all, they are asking you the net force apparently for the charge Q. So I believe that is this one on the top they are referring to. And the others are negative Q, 2Q, and yes, you are going to find this one. The thing is, force is a vector, so what you need to do is find the individual force, and you would want to combine them afterwards. So what I do is I find the F1 first. So F1 here, and we can find from using the usual again the Coulomb's law, just substitute that into it, and again Q is 3 micro Coulomb. So then you can substitute, and then you should find this answer. Same for F2. That you use the same way to do. It's just a distance. Be careful. Is this direct distance, which you can find by Pythagoras theorem. 3 square plus 4 square square root, which is 5, and that's why I got 5 cm here, and you get the answer here. And after you get these two magnitude, what you have to do next is to combine them, and that is something you learn in chapter 1. So what you could do is first of all, what you have to do is, since you know blue one F1 is perfectly vertical downward, and while F2 can be decomposed vertically, which is upward, and horizontal. Let me draw it out. So vertical and horizontal. So I call the vertical one as F2y because it's vertical, right? So and then you can use the sine theta because you can find the theta here, and this is theta also, all right, because of the I don't know how you call it, alternate angle or corresponding angle, whatever that is. And then you can find the vertical component of F2, which is 38.8. And since they are opposite direction, this is upward, this is downward, so you have to minus them, and you get the pure vertical force, which is 51.1. And after that, you can get this to use the Pythagoras theorem, again what you learn in chapter 1, together with the horizontal one. And for now, horizontal one is just this one, which you should take cosine theta instead, and you can find the net force, which is 72.7. For the angle, if I name the angle to be fine, I think how I should define is, because we actually know that the force somewhat should be somewhere here, right? So then this should be fine. All right, the symbol is called fine, and then that will be 44 degrees by using tangent. Okay, next question. I like this question actually quite a lot because it's actually quite inspiring. Okay, so the question is saying that if there are two people, like ordinary people, each of mass of 60 kg, 10 meter apart, and assuming each person is made of water, which is of course not true. I think 60%, I don't know, I haven't Googled it, but you can try. I think 60% or so is made of water. And so we are assuming all the mass right now is made of water. So how many electrons are there in each person? So some background knowledge that you need to know is that water, of course, first of all, is H2O. It's common sense, I think all of you know. For the electron, hydrogen has 1 electron, oxygen has 8 electron. If you study chemistry, surely you know. And therefore, for H2O, 1 water molecule, you have 10 because 1 times 2 plus 8 is 10. At the same time, there is something called molar mass. That is something you will learn in chemistry or in physics in the future in chapter 3. But the basic idea is there is something called mole, right? Which the way that it works is a bit similar to Coulomb, but instead 1 mole is 6.02 times 10 to the power of 23 number of certain things. Okay, so it's a bit like when you go to the flower shop to buy flowers, 1 dozen is 12 flowers. All right, same. All right, so this is a certain equivalent way to calculate how many moles are there. So in that case, if you know that molar mass is 18 grams per mole, that means for water, whenever you can weigh 18 grams of water, that is equivalent to 1 mole, given that of course this is pure water. So what you can do is first of all, finding one person, how many moles are there. And if you are not sure how come I do divide instead of multiply or etc., why not the other way around? Look at the unit. This is kg, this is kg, and this is gram. So if you times it with 1000, it becomes gram and they cancel out. And then if you divide the mole negative one, it becomes mole. So this is how you can do it. So around 3000-ish mole, and then you multiply with the number so that you can turn it into an actual number of how many molecules are there. So this is how many molecules are there, H2O molecules. And like I said, for each H2O, you have 10 electrons, and so you have to times 10 to get the number of electrons. So this is for part 1. Part B is asking you, this is the best part, like after you get the answer from part A, asking you to estimate the electrostatic force. That means using the Coulomb's law to find the repulsion between the two people due to the electron. So it's nothing special. It's just you have to be careful with the charge, because the answer you find from part A is actually number of electrons. And when we use Coulomb's law, we have to use apparently Coulomb for the unit of the charge. So that's why you have to multiply that with the antimetric charge, which is again you can find from the data booklet. And then after you multiply everything, of course you are given the R as well from the question, and then you should be able to find the force, which is extremely large, 10 to the power of roughly 27, which is impossible. Of course, there's no way that if this is the case, then everyone would just repel each other. There's no way that you can live on Earth at all. So part C is asking you what kind of assumption that we have to make the estimation possible. So first of all is apparently we are assuming the only water presence in our body. At the same time, there's only electrons. That actually means there's no proton at all. And this is one of the biggest assumptions. Number 3 is saying that we are assumed to be a point charge, because in fact when the charge distribute differently, that it may affect the force a little bit. But I think the most important is there's no proton. So point charge actually means that it concentrated at a point, so similar to center of mass. And lastly, they are asking you, so how come these forces not observed in practice? And that apparently is something to do with the proton, because proton, with the existence of proton in our body is in fact neutral, and since apparently our body is neutral, then there's no Coulomb's force between any person. Number 7 is actually the simplest question. It's just asking you electric field, and just recall the equation, and you just substitute F and Q into it, and you find the answer. Just be careful with the unit. That should be Newton per Coulomb. Question 8. That is a question involving vector again. So one thing that I would like to remind you before we start is the thing that we are calculating, net electric field strength more precisely, is a vector, because if you look at the equation, it's calculated by F divide charge Q. Okay, so F in itself is a vector, so quite likely, and of course it is true, that electric field is vector. So you have to consider the direction, and if the direction is opposite, they would cancel out each other, unlike the other thing. The other thing that we talked about earlier was voltage. Voltage is scalar, or you may call potential difference, electrical potential difference, and they are scalar, and in that case you don't have to care about the direction that they are giving to you. You just have to add them up together. So this is something that you need to be careful. So for this one, what you have to do is first of all, you really have to understand the idea of vector quite well. So the diagram already given to you that there are two forces acting on P as a test charge given by these two red charges. So since all of them are positive charge, then all of them will just repel each other, and that's why you get the two green arrow like here. And so if you want to find the resultant or net electric field, it will be very similar to finding out the net force, and then you divide it by the charge of P, which of course eventually will get cancelled out. So if you look at these two arrows, you'll find that they are symmetrical. Okay, symmetrical, vertically symmetrical. That means if you try to decompose them, then the one at the top will have one on like going upward and to the right, and the one at the bottom, this green arrow, will also have a horizontal force going to the right and then go down. So these two vertical, one up, one down, these two will simply cancel out. So that's why, so that's why you don't have to care about them, and that's why you see I took cosine theta, because I define this angle as cosine, and the angle could be found by using tangent, cause by looking at the geometry. D is 30 and this is half, so this is 5. You can find the angle by yourself, and then you can then use that for finding out the component. And so from all these things, oh, actually also the R as well. For the distance, it's talking about from the red ball, well, red charges I should say, to P, and that is again by Pythagoras theorem, and it will be 30.4 cm. And so after you get everything, it's like cooking, you prepare all the ingredient, then you can put it into the equation, and just a little bit careful with your calculator, and then you can find out the answer, okay, which will be 3.8 times 10 to the power 5 Newton per Coulomb. Question 9. Question 9 is trying to change one of the charge to -2. So actually I think I do the opposite, but that's fine. I just realized they said that change the top charge. I think I changed the lower charge. Yeah, I think I did. So I think the diagram should actually be flipped. Alright, but anyway, okay, I hope you can understand that. So I actually thought that is the bottom one got changed, and therefore you have these as negative, and which is an attractive force to this from P, and for the top one is still the same. So if you look at the idea of what I have just mentioned for previous question, then for each force here, for let's say this blue one, you could have a force that go to the left, going to the bottom as the component of this blue force. For the green one, then you have one on the right, the one on the bottom. So again, these two horizontal one will cancel again because they are just symmetrical when you look at their value. Alright, they're both 2. So the resultant will simply be the one that going down, and that's why again I times 2 here. Alright, and the rest is just very typical stuff, where again the charge of P is cancelled out. That's why they didn't tell you anything about P. You don't have to care about that. And yeah, this is how you can find the answer for question 9. Question 11 is a good question that help you to revise the idea of current in the microscopic view. That means with this equation. Part A, actually I like part A very much because it's trolling. Because it's asking you the current when they given you that the current at like the earlier was 1.2A. So what is the current at this position? And the answer is still 1.2A, and that is again something I explained in the previous video. You should know that the current remains the same. The other thing that I haven't mentioned, and I somehow recall that is a really simple explanation of why the current is the same, is because think about this. If you remember in year 10, you learn in IGCSE, this is a simple series circuit, alright, where the current will come out here. Let's say this is 10 ohm, this is 2 ohm. Then you can imagine, well, when you say resistor, you can imagine that they have a different radius or different cross-sectional area of wire passing through it. So if you put an ammeter here, or here, or here, they all measure the same current no matter what, and this is for sure that you could accept in year 10 that this is a series circuit, there's only one path, so the current must be the same. But if you look inside, you'll find out if again these two resistors are acting like the wire, then they will have different area, and in that case they will have different drift velocity. So I hope this will be a better or more straightforward explanation to you, and not to mention the conservation of charge or conservation of mass flow. Okay, back to part B. Since we now know the currents must be the same, then we can say that using the equation NAV times Q for both sides, and I put them with the numbering 1 1 1 1 2 2 2 2, just to be a bit more like neat and systematic. And of course you should know that the N is actually the same because they are the same material from the same wire. Of course it's same material. At the same time we are talking about electron, and so Q charge from each charge carrier must be the same, so it's more about A times V, and in that case you should be able to find the answer. Again, it will be very slow and it's very normal. Next question, we have a more straightforward question, actually, this one. All right, very simple question. So we again use the equation I equals to NAV times Q. We know I from the question, and we know N from the question also, and then just one little thing, as we always see already, this is radius given from the question, and so for area is pi r squared, and lastly for the Q you have to find from the data booklet, elementary charge, and that's how you find the answer. For 14, oh, so sorry that I forgot to tell you that you may actually skip part A or B because it's actually something that I mentioned earlier as well, but then if you don't know how or why, that's okay. But for A and B you cannot, okay, I say again, you cannot use this equation to help, because it's different. That's actually the charge are laying outside. You can imagine the charge are laying outside, and within the sphere, as I mentioned, I think earlier, something called the Gauss law, that it would actually make the potential inside zero, as if, again, when we talk about the Earth shell, when you go inside, the mass from everywhere, when they add together, it will all cancel out. It's quite funny, given that it's perfect sphere, of course, perfect sphere. Then all the mass will cancel. You know, every part of this shell will try to pull this person towards that, and eventually they will all cancel out, no matter where you are. So the same idea applies here. So that's why only C and D got a non-zero value, which you can simplify by using the equation that we learned in the video, and then just apply them. It's nothing really special. But what I want you to do instead, you can see there's a bonus question asking you to plot the graph of electric field strength against the distance r. So in fact, you can try to look at the equation here. We could have E here as the y and r here as the x axis, and so you can see that they have we call inversely proportion to the, I should say E is inversely proportion to the square of r, like the quiz that you did in chapter 6. So that's why it is a curve. If you don't know that why that is a curve, or why y equals to k over x squared is a curve, you can try to plot it on your graphical calculator. Okay, so that's all for 5.1.